Hi, my name is Shad, and I'm going to be your teacher and guide today for this course on software reverse engineering. So that's the technique of taking code that's already been compiled and reversing it into something that you can manipulate. So that means you might see the source code, or at least you will be able to see the assembly language and then make any modifications or understanding of what the program is doing. So this course is taught in 8 pieces. In part 1, we'll talk about numbering systems. So if you have not seen binary numbers or hexadecimal before, this will give you a great start into how you can understand what a reversed piece of software looks like. Then we'll do some experiences to get you used to the idea of software reverse engineering, the first attempts. Then we'll have a session where we compare the different tools that are popularly available. And of course, we're looking for free tools, but there are commercial ones as well. And then we'll talk about the reading the stack feature. So this is understanding a program as it's running and doing some debugging while it's in action. Binary patching is about taking a piece of software and modifying it, even if you don't have the source code. And so you can patch things to fix errors or to maybe bypass a certain feature like a login screen or a registration screen. Recognizing code patterns will give you a more in-depth advanced feature of how you can see maybe malware and diagnose what it's doing. And then anti-debugging techniques is the ability to take a piece of software who is trying to hide from you. So this is a cybersecurity topic where we are looking at software that knows that you are reverse engineering it and you're trying to avoid that. And that's this video here right now. And then finally, we'll do some fuzzing techniques. So this whole course here is about software reverse engineering. Now, the guides that are going to take us through here are from Dakota State University. So Michael Ham and Andrew Kramer are both the teachers. So let's get started with this section right now on software reverse engineering.
Okay, and we're back. So I'm going to talk through some anti-reverse engineering techniques that could be applied in a Linux environment. Actually, several of these would work on any platform, would be platform agnostic, but I have implemented them under Linux and some of them are Linux specific. I also have example code, C files and compiled binaries that demonstrate all of these techniques, and I have pushed those to the GitHub repository that you all downloaded earlier. Mike, I hope that's okay that I pushed stuff to your repo.
Give me 1 minute.
Uh-oh. So pull that repo before you...
The problem is they don't have the SSH keys on their VM setup, so I'll make it public so they can...
So they can't pull if... Oh, I understand. Okay.
I'll make it public for
Perfect.
the rest of the day, and then we can flip it.
You're awesome. Okay, so slight problem that Mike is working to resolve. You should be able to simply execute a git pull to get all of these binaries, which is not critical as we talk through them. I could just kind of discuss them and you can go find them here later, but it might be useful for you to have those during the lecture here. So Mike, let us know when that's ready and I will instruct folks how to retrieve them.
Sounds good.
Actually, it's pretty easy. From within this directory, once Mike says to go, you should be able just to run git pull. And after running git pull, in the binaries directory, you should find another one called Andrew anti-RE examples. And there's 11 C files and 11 binaries in there. Those are the ones that Al will be discussing here. So I'll tell you what, while Mike's setting that up, and again, once he's done, the command is just git pull. Should be that easy. While Mike is setting that up, good to go? Can anyone confirm you were able to pull the new version?
Which reaction is that?
Kali, probably. Yeah. I guess Remnix as well would work if either or. Probably Kali. Yeah. Anyone confirm that that works? Excellent. Good. So from within that directory, just in the root SRE MH summer 22 directory, just execute a git pull. It should resolve deltas and do a bunch of other stuff. Any trouble with that? Did it not work for anybody? Anyone need a hand with that?
Oh, Yeah, and you're on their desktops, it's just called Git.
Oh, my apologies. Okay, yeah, on your desktop, the folder here is probably just called Git. You'll know you're in the right place if you have these files and folders in that directory. So go to that directory and execute a git pull. Does it look like it's working for everyone there? Okay, I'm going to go ahead and start talking then, and if you have any trouble, throw a hand up. I'm sure Mike can help you out. So I want to just drive a point home here first. This is something that I think we've discussed once or twice already, but when it comes to anti-reverse engineering techniques and bypasses, in my opinion, we can debate about this, but in my opinion, the reverse engineers always win in the end. It might take work, it might take time, it might take a lot of effort, but ultimately a program has to do something eventually, and in doing something and unwrapping all of those layers of indirection and encryption and whatever it has going on, ultimately it has to do something, and that is going to be observable. So a reverse engineer is probably going to win in the end. So that being the case, the goal of anti-reverse engineering techniques is not to make it impossible to understand what a program does. That in and of itself would probably be impossible, but rather to slow down a reverse engineer and just make their life harder. And I would draw a parallel here between anti-reversing techniques and safe cracking or safe protection techniques. So when you buy a safe at the store, all safes are ultimately penetrable in some way. All of them can be compromised, but they're usually given a rating, and that rating says, here's how well the safe will perform against fire or against hardware attacks or against somebody just spinning the dial over and over until they get the right number. Safes are rated for an amount of time that an attack would take to succeed, right? And so I think anti-reverse engineering techniques are much like that, in that we can make it much more difficult, orders of magnitude more difficult, but nothing can ultimately keep the reverse engineer out. So I think that's a good parallel to draw. So I'm going to show you 11 techniques. In that folder that you just did a git pull on, if you look in Andrew anti-RE examples, there are 11 C files. They're not in the right order because 10 and 11 appear at the top. I should have put 0 in front of all of the single digits, but you get the idea. There are 11 C files there, and those correspond to the 11 techniques that I'm going to demonstrate here. The static analysis techniques should be platform agnostic. These would work on Windows or OS X. The dynamic analysis techniques, some of those are going to be more Linux specific, and then VM detection, I show it in a Linux specific way, but this should be platform agnostic as well. So let's start with anti-static analysis. To understand why these anti-static analysis techniques work, we need to think a little bit about how a tool like IDA or Ghidra is going to examine the binary and what it's going to do to figure out what that code is trying to accomplish. So there are two kind of algorithms that these tools will use, and from my understanding, IDA and Ghidra will do some combination of each, but either or works. One is linear sweep. And with a linear sweep algorithm, we're going to start at the top of the binary, just start disassembling instructions, and move down through the whole binary until we've disassembled everything. Advantages of that, we're going to cover the entire text segment of the binary. Disadvantages, we're not really getting any information there about where the code might jump or how the control flow works, right? So another algorithm that sometimes these tools will use is recursive descent. And with this, we're going to start at like the entry point, disassemble until we find some branching instruction, a call or a jump, go and disassemble that until we have a return, and keep disassembling. The advantage of this is that we get more information about the control flow. We can build a graph from that, but we may miss code caves or like sections in the text segment that look like they're dead code because there's just no direct branch or call to them. So this is something that we're going to try and exploit when we make static analysis more difficult. The other point that you need to understand here for this to make sense is that with x86, instructions are variable length, meaning that the number of bytes that represent each of those assembly instructions is going to differ. 1 byte, 3 bytes, 5 bytes. There's one that's 6 bytes long, right? And instruction size can vary. These can get very large, like 10, 20, actually I think theoretically infinite in size because you can pad a byte 66 at the beginning or something. So we have a variable length instruction set. That is not true for all CPU architectures. Can anybody think of a CPU architecture that does not have a variable length instruction set? ARM. Yeah, ARM's the most obvious. And I think actually maybe PowerPC also. Is that accurate? Don't quote me on that. Maybe. Somebody Google that. So, what I'm going to exploit here is the fact that what the instruction does is dependent upon where I start decoding it, right? If I start decoding right here and I say, this is my instruction, that has some meaning. These 6 bytes have some meaning. But a C3, okay, can anybody tell me what C3 is as an x86 instruction? It's a return, yeah, absolutely. In fact, look, there's one at the bottom. A return, that means something different. So if I point the instruction pointer halfway through the instruction, all of a sudden the meaning changes. And this is useful for like finding ROP gadgets or some of the software exploitation techniques that we could talk about later. So with those 2 facts in mind, here are some ways that you can, kind of organize your code in a clever way to make static analysis more difficult. Technique number 1, if I have a bit of data that I want to hide, and I don't want it to look like there's just a direct reference to a string that's being printed, or a password, or a key, I could hide that data within the code in between some of the instructions, and then simply jump over it and reference that point in the code as my data. Now this is unusual because a string like hello should not usually appear in the text segment mixed among the CPU instructions, but it's just another bit of memory, right? We can read that and use it as a printable string just like anything else. And so one thing that, I don't know if malware so much will do this, but I've seen this in CTF challenges and some other areas. If you use a call instruction, what else does call do besides jumping to the target location?
Places the return address on the stack.
Pushes the return address onto the stack, right? Call will push the address of the next instruction to jump to onto the stack. If I execute a call 12, that means that the pointer being pushed onto the stack is actually going to point to this byte right here, isn't it? Because that's the next quote-unquote instruction to be executed. If I then call another function, at least in 32-bit mode, that thing on the stack will be treated as a function argument, and I can then use that to print out the string. So here, assuming that the EDX register pointed to like a puts or a printf, this series of bytes would end up printing hello you want, right? But when we look at this using just a linear sweep algorithm, it looks kind of strange, and this is going to be hard to read and understand because that's not immediately obvious until you run the code, that this call is just calling right here, right? But here we have our hello. So that's an interesting technique to hide data. Now, I have slides. I can share these slides as well to like how to defeat these techniques, but I think given our time constraint, we only have 30-something minutes left. I'm just going to talk through them. But I'd be happy to show you how to defeat these techniques later if you're interested. So technique number 2, building on that idea, I can hide things in the code that instead of hiding like printable strings that I don't want to reverse engineer to see, I can use those junk bytes to trick the disassembler into thinking an instruction does something that it in fact doesn't. So here I have a JNE $+5 and a JE $+3. Can anybody tell me what a JNE and a JE, both pointing to the same location, effectively do? It's like guaranteed to jump, right? JNE followed by a JE is guaranteed to reach that point. We will never execute this byte 68, but the reverse engineering tools don't know that, right? They can't infer that this series of instructions is guaranteed to always land here logically, so they just keep disassembling, and in this case, we have the byte 68, this X, which is in front of a push and a pointer, and now the tool thinks that that is a call followed by an add, right? So I've added an extra byte in between that will never actually get executed, but now tricks the disassembler into thinking that the code does something that it doesn't. Does that make sense? So I can use that to hide data. I can also use it to confuse the disassembler. So again, I have steps for defeating this. I can show you later. We don't have enough time here now. So another thing that I've seen done often is obscuring function pointers. So let's say that I want to jump to the address 08049176. Maybe that's a function that I'm going to call and it's going to do something malicious. But I don't want the recursive descent algorithm to see that as it's scanning along, there's a reference to a function over here that it should go look at as well. I can encode or encrypt, I'm going to use that term loosely here, encrypt that pointer in some way that makes it impossible for a static analysis tool to infer where that jump is going to take place to, right? So here, I've just used a bitwise not. This is like the bitwise opposite of the other, and we move that pointer into a register, we do a not EAX, and then call EAX, which will have the effect of calling 08049176, but isn't immediately visible to a static tool. All right? So that's a nice trick. That's a good one. So another technique that you might see to hide code from a reverse engineering tool is adding in a false return. So we're going to have to look carefully and think for a minute to see how this works. This is not immediately obvious. But I have a call $+5. Call with a pointer after it is a 5-byte instruction. So a call $+5 really just calls the next line of code. Basically, this calls the add. Right? Remember, a call also pushes a value onto the stack. So after I've pushed a value onto the stack, if I add to that value on the stack, where ESP is pointing, 5, which is the difference between the length of this instruction and here, these instructions will just simply execute in order, pushing something onto the stack, adding to it, and then returning to it, which just executes the next instruction after. This is, I don't know, hard to see without walking through it in a debugger, but trust me when I say call, add, and return, we'll just continue executing one by one as if nothing else is happening. That sort of makes sense. We call the next instruction, we modify the return address on the stack, we return to it, and that return address is the next instruction after. So what this allows me to do then is I can hide other code below that, which we will fall into. We'll continue executing this after, but because the reverse engineering tool's algorithm sees this return and goes, oh, the function's over. I see a return. That must be the end. It doesn't understand how the code is actually going to continue on there, and it just chops the block off right there. So I have a CTF challenge in the Crack Me section in your CTF that implements something like this. In IDA, if you see like stack pointer analysis failed, that's a pretty good indicator that something is wrong with this binary. You can engineer it so that that won't even show up, but this is a good technique, right? Hide data in amongst the code. Okay, so those techniques all apply to static analysis. Let's talk about some ways to defeat dynamic analysis. And dynamic analysis, I mean like defeat debugging, defeat something that's introspecting the program while it's running. This technique is specific to a Linux environment, but sort of does the same thing that Mike showed with the isDebugger present. We're accomplishing the same result here. So under a Linux system, debugging a process really means p-tracing that process. P-trace is the system call that says, I would like to inspect this other process as it's running, observe its registers, interact with its memory, to p-trace a process is like attaching a debugger. But Linux enforces p-trace exclusivity, meaning only one process may p-trace another one at once. Like I can't have two debuggers both attached to the same program. So we can exploit this to figure out if our process is being debugged. We can infer that. The way that we infer that is we p-trace ourself, our own process, and if that succeeds, that means that no other debugger is attached. If that fails, somebody is already tracing our process, and we just exit, right? So I will actually run this. This is a fun example to see. This is number 5. So if you would like to follow along with me here, this is 5.bin. So if you run 5.bin, oh wait, it's in the Andrew RE directory. Binaries, Andrew anti-RE. There we go. If you run 5.bin, it says evil. But if we start it up in GDB, so we'll do GDB 5.bin, and then we'll try and run it, it says we're harmless, all is good, nothing's wrong, nothing to see here, move right along. Can anybody tell me how we would defeat this? Like, if I wanted to continue seeing the evil that the program might do, sorry, I keep walking away from it. How would I defeat this from within GDB? What have we learned that would apply here?
Is there a register that you can edit?
Yeah, probably so, right? I mean, if you look at the code that we use to accomplish this, it's really just an if statement. If I edit 5.c, at some point the program needs to call ptrace and then check what it returned. So this is the same principle that we use to bypass the product code, or Mike had another example. Yours wasn't a product code. What were you doing there?
I can't remember.
Oh, you had isDebugger present, right?
Yeah, just the isDebugger present.
Yeah. Yeah, so there's no reason that we couldn't single step through this. And if I know for a fact that the program is going to check if there's another process attached to it, I could pause it right there, modify those registers, or even just mop out that jump. Should work great. This is another great example of where, like, running something in a sandbox in an automated environment to check if it's malicious is helpful. But if you run it through that sandbox and it goes, I'm harmless, that doesn't necessarily always mean that it's going to be. Having some manual intervention and having a reverse engineer look at it and know that is going to help you find things that you otherwise might not. So this is kind of analogous to Mike's isDebugger present example. This is just what you would see in a Linux environment. Okay. So another thing I think people don't hear about very often, did you know that main is not necessarily the first function that runs when you run your binary? We all think main's first. Actually, there's a function called libc start main, at least assuming that we're using standard C library, and that calls some constructor functions if they exist, and after those constructor functions exit, eventually main gets called. So oftentimes we'll start our reverse engineering efforts at main because this is clearly all the program does, but most compilers, and this is how you do it in GCC, but most compilers support the ability to add constructor functions that will execute first. So in this case, with the 6 binary, we have a constructor function called init, which executes something evil and exits. But if I was to open this up in IDA, that's all I would see first, and might just make the assumption that's all that the program does. Right? So this is something to watch out for. Let's see. So our program could also scan for breakpoints in memory to check to see if a debugger is present. Now this is only going to work if we're single stepping through a program or if we have applied breakpoints on our own. But we can scan our memory for those breakpoints and if we find them, assume that a debugger must be present inspecting the process. The way that breakpoints work is there is an instruction int3, which is the byte cc, that's an int3 instruction, and it's an int3 is a software breakpoint. It generates a, what would you call it, a trap? Like it raises a signal, right? Pauses the process. When your debugger wants to implement a breakpoint at a certain instruction, what it actually does is overwrites that instruction in memory with a cc byte, keeps a reference to what it overwrote, executes until it hits that cc byte, pauses, quickly swaps that back out so that it all looks the same to you, but behind the scenes, there was a cc somewhere in memory in order to implement that breakpoint. So what we could do is like, let's say that we get a reference to our main function. So here I have a pointer to main. Volatile just means like, this might change at runtime, so don't make any assumptions about what that pointer is going to be when you compile the code. And then I'm just going to look through the first 32, hex 20 bytes in main, and if I find the byte cc within that block of memory, I'm going to exit assuming that a debugger is attached. If not, we'll just continue on. So let's walk through this one as well. I think this is a fun example. We can do it all together here. This was number 7, right? So we're going to use 7.bin. So if I just run 7.bin, it's going to say hello world, all is well, nothing's wrong. But let's open up 7.bin in a debugger. So we'll do gdb 7.bin. Now, I'm just going to go ahead and type run. Just let this execute. And it still just says hello world. Assuming that 7.bin is scanning for that byte cc, and I am in a debugger here, why do you suppose it didn't detect the debugger? Why didn't it?
No breakpoints.
Yeah, it didn't add any breakpoints, right? So it's not necessarily detecting that there is a debugger watching it, it's really just watching for those bytes cc. But, and boy, I hope this demo works. I didn't test it before I walked up here, but it worked in the past. If I do break main, so put a breakpoint on the main function, and then I run it again, there we go, debugger detected, right? And the way that it did that again is it scanned that block of memory where main's instructions are, saw that that byte cc had been placed in there, and makes an assumption that the debugger is present. When do you suppose this could go wrong? Like if I'm implementing this in my program and before the program runs, I scan the whole text segment, all of the code for the byte cc. Could I ever make a mistake? Could this go wrong? How and why?
What's the ASCII character for CC?
Right?
What is it? I don't know.
Well, it's actually beyond 128, so it exceeds the 7-bit ASCII range. But it's like in Unicode, it means something, right?
Some special character in Russian.
Probably, yeah. Yeah, or, you know, if we, well, that's not going to work. How do I get like a hex dump of main? Does that work? Okay, that doesn't work. Let's do object dump, -d, -m, intel, 7.bin. Like, there could be a CC byte in any of the following bytes of an instruction, right? If that CC byte was part of a pointer, just based on the offset that was calculated at compile time, it's entirely possible that one of those bytes will appear, even if that was not the first byte representing that actual instruction. So I would say this is harder to implement from the attacker, the anti-RE perspective, but it is possible and it is a cool technique if you can make it work. That's why I only scanned the first 32 bytes, because I assume that beyond that, there's probably going to be a CC somewhere, right? Any questions?
So I looked it up. CC is an accented capital I.
Ah, yes, the accented capital I. Is it like with the umlaut over the top?
It's just a backslash, like a tick symbol.
Huh.
I have no idea what language that is. But
There you go. Yeah, so that CC byte could very well appear in code or in data, either way. Yeah. So we can actually exploit this int3 instruction in kind of a more humorous way if we really want to troll a reverse engineer. I would say this won't prevent you from understanding or reading the code, but boy will it make it hard to debug. If you just pollute your program with int3 instructions, it makes it impossible to debug because it pauses every single time it hits an int3. This is sort of the same problem in reverse, right? Just make it impossible. We would probably have to write our program at the assembly level to make this work. There's no real easy way other than those inline assembly things in C to add that in C code. But you could theoretically build a compiler that would add an int3 between every single instruction and just make your life a nightmare. Let me show you what that looks like when we run it, just because this is funny. Let's see. So if I run 8.bin, all is well, everything's fine. Oh, and by the way, in order to accomplish that, in order to make it continue executing just fine, you need to have a signal handler that will catch when that int3 signal executes, catch that and just do nothing. But assuming that you do that, your program runs just fine, everything works, until you run it in a debugger. So we'll do gdb 8.bin. And I'm just going to type run. I didn't set any breakpoints. I didn't tell it to stop anywhere. And it pauses. Like, dang it. So I do continue, and it pauses. Continue, and it pauses. Like, no, I'm serious. Continue, and it pauses. And you could imagine that would make it really, really frustrating to reverse engineer a piece of malware.
Can you print out all the breakpoints?
You could, yeah. So in order to defeat this, I would say it's not hard to defeat this. It's just time consuming.
It's just trolling.
Yeah.
So if you tried to show your breakpoints, what would it show?
If I tried to show the breakpoints?
Yeah.
Oh, I don't think that it will actually show them because the debugger doesn't have a list of those in its table. Like if I run this again and do, is it info breakpoints? None.
Okay.
Because a breakpoint is a table of like where those CC bytes have been overwritten combined with the CC that stops it at runtime. But the fact that those CC bytes exist doesn't imply that there's a breakpoint there. Yeah. What's up, Mike?
If you open that in a hex editor and searched for all of the CC bytes and replaced them with like a knob, would that be a valid way to defeat that check?
Maybe, but could cause some problems. So yeah, let's think about that. If I open this up in a hex editor, I like hex curse. Oh, but I don't have it installed on this computer. Do I have hex editor installed? Okay, we're just doing hex dump. R2, there you go. Love it. XXD, the old school way. Okay, so I'm going to open it with R2, and then I am going to enter visual mode, right? There we go. Yeah. So let's say I wrote an R2 pipe script or a Ghidra script or just a Python script to search through this binary, find all of the instances of hex CC, which we know is an int3, and overwrite them all with what byte? What would be a good byte to put there instead?
90.
Knob, yeah, 90. 0x90, just a knob. What problem could I cause though? Like what could go wrong there?
Override a real CC.
Yeah, right? Like what if there's an I with an accent that was important to the program? Or what if that byte CC was part of a pointer for a call or a jump instruction? Now I've broken the functionality. So really what you would need to do is write some sort of intelligent replacement algorithm that will disassemble all of the code, find where those CC bytes exist, and overwrite them. So combine this technique with the fact that we can misalign our instructions and insert data that's not actually there and confuse that disassembly algorithm, you could make it really, really difficult to reverse engineer a piece of software.
So how does the debugger handle, I guess, naturally occurring CC instructions?
It will just pause. I mean, that shouldn't appear as an executable instruction unless we had the intent for a debugger to pause there, at least as far as I'm aware.
Or, I mean, it could appear, right? Like you said.
Yeah, but I don't think a compiler is going to insert that instruction unless you intentionally told it, like, I want to raise this signal here.
Oh, I see what you mean. Okay.
Right?
Yeah.
So the CC byte could appear, but it would be in another instruction or for another reason. As far as in that linear disassembly output, probably a compiler wouldn't do that unless you told it to. Yeah. Okay. So, what else do we have here? Oh, and this one is a duplicate of Mike's technique. Great minds think alike, Mike. RDTSC, we've already covered, so I'm not going to dwell on this one very long. But of course, this works under Linux as well. And look, we must have been referencing the same bit of code when we were learning about this. I think that this XOR ECX with an add of the difference, or no, this is the original time to ECX. I think that might be from the Practical Malware Analysis book. Do you have that book? Were you reading it when you?
That might be where it came from.
I'm pretty sure you know the Practical Malware Analysis book. It's a red book with an alien on the front. I'm pretty sure this technique is discussed there, and that's probably where I got the code. So
I was trying to figure out why we did that.
should look in the PMA book. That might be it. So I won't dwell on this one any longer, but I mean, like with anything else, you can defeat this technique simply by knopping out the check or lying to it at runtime, modifying it in some way so that it thinks otherwise. Okay, so bonus technique in between, before we get to the VM detection stuff, here's another clever way that you could make a reverse engineer's life difficult without really modifying your code that much. And that is debugger bugs. Say that 9 times fast. So a debugger is just a program, like any other program, and debuggers are going to have software flaws just like any other, right? They're going to crash, they're going to run into fault conditions, and there have been multiple instances over the past several years of debuggers having crashing bugs that you can reach from just loading a binary into them. So here's a fun one from OllyDebug version 1.1, exploit DB number 388. That's an original bug right there. 3-digit ID. This is probably from like the Millworm days. Yeah, look at that. Before it was even exploit DB. Anybody remember Millworm? That was the good old days. Anyway, so OllyDebug had an issue where if your program called output debug string, a buffer overflow would occur, and this was actually exploitable for code execution on the debugger. So you could like give somebody a program to reverse engineer, they step through it with OllyDebug, and then it causes Olly to execute code in and of itself, which is funny, I think is the technical term. Here's another great example. This one actually was discovered by Josh Pauli, who until recently was a DSU faculty member. And this is a crash in GDB, I think, right? Was that what the slide said? Yeah, GDB null pointer dereference. Josh was fuzzing GDB with the AFL fuzzer that we might discuss later in the day here, and came across a null pointer exception, not like security relevant, right? You wouldn't use this to execute code, but can you imagine if you're trying to reverse engineer a piece of software and every time you load it in GDB seg faults? What do you even do at that point, right? So he reported this, it is now fixed, but I promise you there are many more bugs like this. So if you'd like an interesting research project, fuzzing a debugger or fuzzing an RE tool is likely to produce results. GDB is a very complex tool, and there just are bugs to be found there. So that's a fun one. That's a good one. Okay, and our last two of the day then, let's talk about VM detection. So oftentimes, a reverse engineer is going to put a piece of malware in some kind of sandbox environment and detonate it just to see what it does before undergoing the more time-consuming reverse engineering effort to figure out what it does manually. And so it would be useful for our program to try and figure out if it's in a VM and do something harmless if it's in a VM, and if not, then execute the evil actions it was intended for. So one way that you might be able to detect if you're in a VM is the CPU ID instruction. So CPU ID gives you information about the processor that your code is executing on. The way this works is you put a number in EAX, and depending on what that number is, after executing CPU ID, these registers will contain information about the CPU. The processor manufacturer string, they'll contain like the features the processor has available, there's a serial number, there's all kinds of information that you can get from CPU ID. One of those things is the manufacturer string, and at least under some virtualization environments, that manufacturer string will leak the fact that we're under a VM. So KVM, 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 that's like if you're in a Linux KVM environment. VMware, Microsoft Hyper-V should look familiar, Xen. Not all virtualization tools do this. Sometimes it will show the real processor manufacturer string. So this is by no means foolproof, but this is often used. This can work, right? So just CPU ID. That's a fun one. That's a good one. Okay, and the last technique that I have for you today is one that we have discussed a little bit already. That is checking the number of CPU cores. So most modern machines are only going to have, well, no, they're going to have lots of cores, right? A VM usually is going to have one core. And so if we just check to see how many cores the machine has before running, oftentimes we can figure out if we're in a VM or not. Now again, this is not foolproof. You could have a VM with 2 cores, that would defeat it. Or you could have a standard machine with 1 core, which would be detected as a VM. But on Linux at least, you can just look in the proc CPU info file, and there will be entries for each CPU core. So if I was writing a piece of Linux malware, I might check that file to try and determine if I'm in a VM. In fact, from the command line, you can do this even easier with the Inproc command. I have a, well, you can't see it there. Move this over. There we go. When I ran Inproc, I have a 4-core CPU. But if I run cat proc CPU info, I should see entries for each of those CPU cores. So this is processor number 3. There's 2, 1, and 0. So that was a very quick run through of several methods that you can use to make reverse engineering more difficult. The C files and the binaries that I gave you in that directory there implement each of these techniques. If you want to go play with them, use them in a classroom, feel free to. We have about 5 minutes left in our session here, so I'm going to stop there and give you time for questions or CTF or anything related. So, thoughts on these items?
So could it be possible to measure the time it takes for API calls?
Definitely.
Okay.
Yeah, so here's a fun one, kind of the cat and mouse game of VM detection. It used to be that if you were writing a piece of malware and you didn't want an antivirus sandbox to detect it, you would put the following code in your malware, sleep 10. Because the sandbox is checking the program at runtime. When the user double clicks the exe, the sandbox has to quickly figure out if it's dangerous before letting it run, right? But we don't want to like hold that up forever, because if the user double clicks the exe and they have to wait an hour for the program to start, the antivirus is no good. So if you just sleep for 10 seconds, it used to be that a lot of AV engines would just give up. They'd go like, well, doesn't look like it's doing anything bad, so we're good, no worries.
10 seconds?
Yeah, I mean, sometimes like 2 seconds is enough, right?
Milliseconds or seconds?
Literally 2 seconds, yeah. Yeah, and in fact, I promise you, if you take a piece of malware, write something malicious, upload it to VirusTotal, it'll have lots of detections, add a sleep 10, several of those detections will still disappear today. Not all of them by any means, but if you're detected 40 out of 50 times, it'll probably be 30 out of 50 after that. So, what the antivirus companies did was they said, well, no matter how much you sleep, we're just going to sleep for 0 seconds. We're just not going to sleep at all. But now I can exploit this in the other direction too, right? Because if I sleep for 10 seconds and I do an RDTSC before and after, and I detect that it's only been 100 CPU ticks since I started sleeping, now I know something janky is up, right?
Right.
So it's kind of cat and mouse. It's difficult. I don't know if that answers your question. But.
Yeah, more like, I was thinking more like, I don't know, if you're doing like, I mean, the time it takes for you to access memory in a virtual machine is longer than it's running on bare metal.
That as well, yeah. Yeah, so the sleep technique is just one example of this. Let's say that I try to memory map a file, or I malloc a very large amount of memory. The time that takes will definitely differ depending on if I'm running on hardware or running in an antivirus sandbox environment. Definitely. And I don't know that I can tell you exact numbers, but there will be a difference.
Yeah, I was thinking probably you need, I don't know, maybe some kind of even machine learning to start.
It's a good research project idea right there.
For you.
So literally, if malware is designed to just ignore a VM, you are probably safer from malware if you run a VM.
In a lot of cases, that's probably ironically true. I don't want to stand up here and say, just run VMs, you'll never get hacked. That's not going to be the case. But
Well, there's less
in
damage
some
too.
ways, yeah. I mean, if malware is trying not to run in a virtualized environment, you're going to miss some of those samples.
But you could run into problems where, like, if you have a really complicated malware where it knows it's in a VM, and then it exploits like a 0-day in the VM software,
Break out the host.
breaks out with the sandbox, and then gets into your system.
We're kind of talking security through obscurity here, right? Like, I wouldn't say that's a strong security control so much as just Linux has less viruses because less people use it. So
For good
it
reason.
works. Yeah. Same principle, right? But yeah. Yeah.
This may be a stupid question, but when I use volatility to analyze malware, they tend to print out the suspicious PE in assembly code.
Mm-hmm.
So how should we interpret that? I mean, after learning this, it seems that everything looks the same for me. So how can you interpret assembly codes? I mean, how should we interpret the assembly code printed out by this volatility software? Yeah.
So are you asking in the context of these anti-reverse engineering techniques, can you trust what it shows you?
Yeah, and how should we read? How should we interpret that?
So my advice, if I was doing that kind of work, is trust it until you see indications otherwise. Like, I wouldn't just throw it all out because it's possible that it's wrong. It's probably going to be okay. I doubt that a lot of malware is using these hyper-specific techniques. So I would trust that output until I see an indication that something is broken, and then I would investigate that directly, I think. Does that make sense?
Yes.
Like, these exist, these techniques exist, but you're not going to see them in every piece of malware by any means. I've stolen 1 minute of your break already. We'll give it back to you on the other end. So I think we're going to pause here. I'll hang out, answer questions, help with stuff if needed. Otherwise, have a great break, and we will see you again at 2:30, right? That sound good? Yeah. What's up?
So